Welcome to our presentation on DiffuseKronA. Let's dive into this innovative approach which aims to enhance the performance and personalization of diffusion models while significantly reducing the trainable parameters and maintaining high fidelity. I am Nityanan Mathur from Smallest AI presenting DiffuseKronA on behalf of all my co-authors. Let's move to the key contributions of our paper. Our work primarily focuses on high parameter efficiency, finer control over parameters, and interpretability. Parameter efficiency is a critical aspect of modern machine learning. It refers to the ability of a model to achieve high performance with fewer parameters. This not only reduces the computational resources required, but also makes the models more accessible and easier to deploy. To start, we will compare our DiffuseKronA with LoRA-DreamBooth. Let's take a closer look at the impact of our method using SDXL model. The standard LoRA-DreamBooth technique has around 5.8 million parameters, which our technique reduces to 3.8 million parameters. This in turn implies that you now need to store smaller files for every fine-tuning performed. A similar pattern can be seen using base stable diffusion model as well. Overall, these optimizations have led to an approximate 50% reduction in parameters and model size across the board. This not only makes the models more efficient, but also more accessible for deployment in resource-constrained environments. In this section, we will discuss our key contributions in the terms of control and interpretability. Let's start with LoRA, which stands for low rank adaptation. LoRA is a technique used to adapt large pre-trained models efficiently. Here, we have two matrices A and B, where A is in the space of real numbers with dimensions d by r, and B is in the space of real numbers with dimensions r by h. The key idea is to compute the change in weights, delta W as the product of A and B. The rank error is much smaller than the minimum of D and A, which makes this approach computationally efficient. Next, we introduce the Kronecker adapter. This technique involves two matrices, A and B, where A is in the space of real numbers with dimensions a 1 by a 2, and B is in the space of real numbers with dimensions B 1 by B2. The change in weights delta W is computed using the Kronecker product of A and B. The Kronecker adapter computes Kronecker product, where A and B remain separate matrices with distinct roles. It provides a granular control, that is, you can optimize A and B independently, adjusting each to target specific aspects of the model. The dimensions of A and B are bound by A1 times B1 equals D and A2 times B2 equals H. This increase in variables introduce finer control over the dimension of matrices. In other words, LoRA has only a single parameter R controlling the tuning, whereas Kronecker adapter has two. The Kronecker product, also known as the tensor product or direct product, is an operation on two matrices that results in a block matrix. It is used for constructing large matrices from smaller one without bounding their dimensions. Let's look at an example. Consider two 2x2 matrices, A and B. A Kronecker product, B implies that each element of A scales all the elements of B, resulting in a larger matrix. First, we introduce LoRA's low rank update to the weight matrix. Then, we transition to the Kronecker product representation, highlighting how it expands into a structured 4x4 matrix. Notice the arrow signifying the switch from traditional LoRA to richer parameter interactions. And finally, we highlight the resulting output matrix, showing how the Kronecker operation composes individual blocks into a unified whole. Introductions apart, let's look why and how does the Kronecker product based adaptation beats the standard dot product based LoRA. Rank of a dot product is always less than or equal to the minimum rank of the multiplicants. Rank of the Kronecker product equals the product of their individual ranks. Consider two matrices, A with dimension 3 cross 2 and B with dimension 2 cross 2. Their dot product results in a matrix of dimension 3 cross 2 leading to rank 2. Now, the Kronecker product results in a matrix of dimension 6 cross 4, which leads to rank 4. This multiplicative rank property of Kronecker products is the core reason. Let's look into how we can use Kronecker adapters in diffusion models for personalization. The fine-tuning process involves optimizing the multi-head attention parameters based on the reconstruction loss between the original and the generated images. Now, we inject the small trainable layers to the attention matrices so that only these small layers gets trained. We use Kronecker adapter to build these trainable layers, which allows very high parameter efficiency while capturing more information. Here is our overall training pipeline. We also present a schematic illustration of LoRa versus DiffuseKronA. LoRa is limited to one controllable parameter, the rank, while the Kronecker product showcases enhanced interpretability by introducing two controllable parameters, a 1 and 2. During inference, newly trained parameters, denoted as theta, are integrated with the original weights dphi, and images are synthesized using the updated personalized model dphi plus theta. You might be wondering, how well does it actually perform? The answer is clear. The numbers speak for themselves. Let's look into the quantitative analysis of DiffuseKronA as compared to other methods. Observe DiffuseKronA. With configurations like 16 and 64, it already achieves superior parameter efficiency. But what happens when we push it further? Even as we aggressively reduce parameters, lowering to 8 and then 4, DiffuseKronA maintains amazing performance. At 4 and 64, it uses just a fraction of the parameters, yet outperforms LoRa, SVDiff, and others. In the evolving landscape of AI efficiency, balancing model size with performance is critical. First, observe the parameter counts. Vanilla DreamBooth at 980, 2.5 million parameters, sets a baseline for quality but demands immense computational resources. Custom diffusion reduces this to 57.1 million, yet struggles to match performance. Meanwhile, LoRa-DreamBooth and SVDiff push efficiency further 1.09 million and 0.44 million parameters respectively but still lag behind in key metrics. Now look at DiffuseKronA. With just 0.32 million parameters, fewer than all competitors, it achieves the highest CLIP-I score of 0.82, and Dino score of 0.73. Even against SVDiff and LoRa, DiffuseKronA delivers superior consistency, reflected in tighter error margins. Similar pattern can be seen with SDXL as well. You might be asking, but what about the qualitative impact? The answer lies in the stories, the narratives, and experiences reveals it. Quality is the ultimate measure of a model's effectiveness. Let's examine the results across various creative prompts. For instance, when generating a sculpture holding flowers, DiffuseKronA produces strikingly detailed and coherent outputs, surpassing the competition in both realism and adherence to the prompt. Take another example, a plushie on a skateboard in Times Square. Here, DiffuseKronA not only captures the whimsical nature of the scene, but also maintains high fidelity to the input image, outperforming LoRa-DreamBooth and SVDiff in both creativity and precision. In more complex scenarios, such as a dog in a swimming pool, DiffuseKronA again leads the pack. Its ability to retain fine details, like the texture of the dog's fur and the water's reflection, sets it apart from DreamBooth and custom Diffusion, which often struggle with such nuances. Across diverse prompts and scenarios, DiffuseKron consistently delivers superior quality. Its ability to balance creativity, detail, and fidelity makes it the clear choice for high-quality generative tasks. A major question lies ahead. Even though the numbers are good enough, is the method stable? This image vividly demonstrates that DiffuseKronA consistently produces high-quality images across a broad spectrum of learning rates, all while maintaining impressive clip and dyno scores. In contrast, LoRA struggles significantly. It fails to generate images entirely at very high learning rates and produces subpar results at very low learning rates. This stark difference highlights DiffuseKronA's robustness and versatility compared to LoRa's limitations. Well, so far so good. But what happens when the user has only a single image of the subject, the HF logo for instance? Does DiffuseKronA works? This qualitative comparison explores how well our model perform in single-shot scenario, even with just one reference image. DiffuseKronA excels in generating diverse and high-quality interpretations, such as a logo made as a coin or one with a soft pastel color palette and futuristic neon glow. Having seen all the capabilities, let us also explore how well DiffuseKronA adheres to the given image and text. Let's start with the prompt: a clock with the Eiffel Tower in the background. DiffuseKronA not only places the clock accurately within the scene, but also maintains the clock's unique design details such as the number 3, ensuring it remains the focal point. In contrast, LoRA-DreamBooth struggles to balance the background and subject, often losing key features of the clock. Next, consider the prompt: a toy in a jungle placed on a rock. DiffuseKronA excels in embedding the toy naturally into the jungle setting while preserving its distinct characteristics, such as the red sea, color of car. The toy remains recognizable and true to the input image, showcasing DiffuseKronA's superior adherence to the subject. Text adherence is a crucial aspect of generative models, ensuring that the output aligns closely with the given prompts. Let's examine the first prompt: and I'm relaxing at the ramen shop, enjoying a bowl of ramen with chopsticks and soup. DiffuseKron excels in capturing the essence of the scene. The anime character is depicted naturally enjoying the ramen. In the rapidly evolving field of generative models, achieving state-of-the-art performance requires excelling across multiple dimensions. DiffuseKron beats state-of-the-art methods, whether it's parameter efficiency, output quality, or adherence to prompts. DiffuseKronA consistently outperforms competitors like LoRA-DreamBooth and custom diffusion. Second, it offers more stability. Across diverse datasets and complex prompts, DiffuseKronA delivers consistent results with minimal variance, ensuring reliability in every application. Thank you for your time.